we'll start out by asking what is energy? Can anybody tell me what energy is? Anybody have ideas?
Um, Accumulated like force or I don't know, something like that.
Okay, well, so that's a really good thought, right? Um, we're going to actually talk about how force is related to energy. So I'm really glad that Sebastian brought that up. Um, any other ideas? So we have a starting point.
Power.
Okay, so energy and power, they are also related, right? And actually, usually that's one of the first answers I get, you guys, because um, like if you think about electricity, right, which is a form of energy, we always talk about paying our power bill, right? Um, so energy and power, they are related, but they're not exactly the same thing. Um, so I'll just pull out our physics definition. All right. Really, what energy is the ability to do work. And that's why we're smushing all of this stuff together. We're smushing energy along with work and power. So, energy is the ability to do work. We're going to get back to that. We're going to talk more about that at the end of the day. Okay. So, I see people looking back up. So, can anybody tell me? Now, this is easier. Can anybody tell me the different types of energy? Just throw out some.
Kinetic energy.
Oh, that is a type of energy. So, kinetic. Here, I'll give you one because I just brought it up. How about electrical energy? Right. So we have electrical energy. It's the energy, in charge, in electrical charges. Kinetic energy, the way that we've talked about it the most in your science careers, it's usually the energy of objects, right? And we'll talk more about this. So, if we're talking about the energy that physical objects have, that's actually called mechanical energy. Any other ones?
Do calories count as energy?
Yeah. So calories is a unit of energy, right? And usually when we think of it, um, like in chemistry, did you guys do the peanut burning lab? Right? And so usually when we think of calories, we usually think of what kind of energy? Starts with a T?
Telekinetic or
No.
Thermal.
Oh, yeah, thermal. Yeah, but so calories, you guys, calories is a unit of energy. We're going to talk more about that. All right. It's the English unit. So we have thermal energy. That's energy from heat. We have mechanical energy. We have electrical energy.
Chemical energy.
Yeah, chemical energy that's in chemical bonds. Um, what kind of energy is allowing you to see me right now?
Light energy.
Yes, light energy. And then actually, here's another one. This also allows us to be alive. Nuclear energy, right? It's what powers the sun. It's actually where you get most of your electricity from. About 70% of our electricity comes from nuclear power plants. So, kinetic energy, you guys, this one we're going to talk about. along with potential. So these are the two main types of mechanical energy that we're going to discuss. So we're going to focus on mechanical energy. But just so you guys know, there are whole physics classes in college if you want to become, say, a mechanical engineer, that are just on energy. Okay, we're just going to spend 2 weeks on it, but I've had to take like 2 semester-long classes that were just on energy. Okay, this is a really, really important topic, especially for your futures, right? I've heard that there's this thing, this global warming thing, right? Because of how we've been getting our energy, we're going to have to switch into different types of energy. So, okay. So there's all these kinds of energies, but we're going to focus on mechanical energy. All right. And the mechanical energy is the energy in physical objects, like macro scale objects. All right. So, like I said, the two main types are kinetic and potential. And kinetic energy, you guys, here, wait, I don't remember what I have on the next slide. So, kinetic energy, just to give you a preview of it, that word kinetic means what? Do you guys remember? No one? So you could have a kinetic sculpture. No, like Calder used to make these. No, you guys should look him up. He has a famous sculpture in the Sears Tower or whatever it's called now, Willis Tower. um, so kinetic, you guys, means moving. So for kinetic energy, objects will have to be moving. All right. Potential energy, that's energy by position. So let's delve a little deeper. Let's talk about potential first. Okay. So first of all, many of you have been misled by your middle school teachers, or maybe even like if you had to take physical science. A lot of elementary teachers, school teachers, and middle school teachers teach that potential energy is stored energy. Okay, it's not. What potential energy is it's energy by position. Because if we called potential energy stored energy, then what would you call kinetic energy? Would it be used up energy? Right? Like it doesn't make sense to call it that. Now we can, just so you guys know, you can store energy as potential energy, but you can also store energy using kinetic energy. So I don't know if you guys have ever heard of a flywheel, but what a flywheel is, it's usually like a big heavy wheel. You get it spinning, and then when you need an assist, when you need an energy assist, you tap into the flywheel. There's energy that's stored into it, and you can use it to do something else. All right. So once again, potential energy, not stored energy. It is energy by position. Now for mechanical energy, it's your position above the surface of the earth. So the higher you go above the surface of the earth, the more potential energy you have. The closer you are to the surface of the earth, the less potential energy you have. It's kind of like, can I bring you guys back down memory lane for a second? So let's think about, in chemistry, you guys learned that there was like a 1s orbital. Do you remember this? And a 2s orbital. And then there was the 2p orbital, right? And these were energy levels. Remember, your teachers talked about them as energy levels, and electrons could move up in energy level, say from a 1s to a 2s. And if they did that, what they did is they gained potential energy because they changed position relative to the nucleus, right? And then you could convert that energy back into light energy, and you could give off a photon of light. Is all that like ringing a bell? I hope somehow. Maybe. All right. So then, so for potential energy, like I said, it's going to be your height above the ground. So our equation, this is our equation. So the potential energy equation is equal to mass of the object times the gravity times the height. Now for us, you guys, gravity is always going to be 9.8 meters per second squared, right? If you want, you could round that to 10. I'm okay with that. So for gravity, remember gravity will always be 9.8 meters per second every second. Although you can round it to 10 meters per second every second. And then the height, this is your height above the ground. Mass is in kilograms. So let's talk about units real quick. So this would be a kilogram. This is a meter per second squared. And this is a meter. Now, I don't know if you guys remember this, but if we break this down, a kilogram meter per second squared, we also called that a Newton, right? And so the units could be kilograms meters squared per second squared, or we could call it a Newton meter. Does anybody remember? For work, let's bring you back a second. Work was force times distance, right? And so that was a Newton meter as well, wasn't it? Okay. And then what was the shorthand version of a Newton meter? Does anybody remember?
Joules?
Yeah, it was a joule. So the unit for energy, you guys, is going to be joules. Now the English unit, which Brandon already told us about, the English unit is calories. Okay, or there's another unit of energy, British thermal units, right? You're most used to calories. So calories is the English unit of energy. Joules is the metric unit. We're going to use joules. So this height, you guys, this is height above the ground. Can I show you a problem now? I'm looking at your faces to see nods. I saw a few nods. Okay, saw a few more. So I'm going to show you this problem. So I have a sledder, all right? And the sledder has a mass of 50 kilograms, and they're standing on top of a 12-meter high hill. So their mass is 50. The hill has a height of 12 meters. How much potential energy do they have? Now we know gravity. Do you guys want me to use 9.8 or 10? I'll use whatever you want me to. 10. All right. Okay, so gravity will just move to 10. And now I want to find the potential energy. So this is very straightforward. Potential energy is mass times gravity times height. And then the potential energy would be 50 times 10 times 12. So that would be 6,000 joules. Is that right? Can someone confirm that with me?
Yeah.
Okay, all right. So the potential energy is 6,000 joules. So that doesn't seem too bad, right? Now, how much energy would they have if they were standing halfway up the hill? Well, if they were standing halfway up the hill, the height, instead of being 12, it would only be 6, right? Now, I could tell you, without even doing a calculation, that potential energy for, well, I don't know, we'll call it part 2. The potential energy would be 3,000 joules. Because there's a direct relationship between the height and the potential energy, right? If you make the height half, potential energy goes down by half. If you double the height, the potential energy doubles. I could prove it by just punching in 50 kilograms times 10 times 6. So if you put in 50 times 10, that's 500, times 6, 3,000. Easy so far? Okay. It's not going to get too much harder. Now, okay, I'm just looking to make sure everybody's done writing. Looks like it. So now for the second kinetic energy. This is energy due to motion. So I'm going to flip back really quick. For potential energy, if your height was 0, you had 0 potential. For kinetic energy, if you're not moving, you have 0 kinetic energy. Okay? Now the equation for kinetic energy is going to be this. Kinetic energy equals 1/2 the mass times the velocity squared. So for this, if I increase the mass, the object has more kinetic. Just like in the potential energy equation. If I increase the mass, the object has more potential. And here you guys see the relationship between velocity and kinetic energy. That's not a one-to-one relationship. You see that? Because it's velocity squared. So if I double the velocity, what happens to kinetic energy? What would 2 squared be?
So it's 4, so it doubles?
Well, it's 4, so it quadruples, right?
Quadruple.
Yeah. You said it right, the first part. So it is 4, so it quadruples. If I triple the velocity, you guys, the kinetic energy goes up by, don't say 6. Yeah, I saw someone mouth it 9, right? Because 3 squared is 9. And then 4 squared, that would be 16, and so on and so on. So actually, this is why I don't know if you've ever noticed this. There's other things going on when you're driving your car. But all things being considered, the faster you go, like on a highway, the more gas you use. I don't know if you ever noticed that. So if you're going 60 miles an hour and you decide you're going too slow and you start going 90 miles an hour, you use a lot more gas when you're going 90 to get to the same place. Why? Because the energy required to make you move that fast, it quadruples if you double your velocity, right? So anyway, let's talk about units again. The units here, this would be kilograms. You guys know velocity is meters per second. If I square it, it would be meters squared per second squared. A kilogram, meter per second squared, is a newton, which would leave me 1 meter left over. So that would give me a newton meter. And we already know that a newton meter is a joule. So the units are joules. Just like potential energy, just like work. They all have the same units. And then remember, if velocity is 0, kinetic energy has to be 0. All right? So, can I do a problem with you with this? Yeah? I'm seeing nods? Okay. All right. So here's my problem. I have a car, and my car has a mass of 1,200. So the mass of my car, 1,200 kilograms. It's traveling down the highway, and it has a speed of 15 meters per second. So the velocity, 15 meters per second. I want to know, how much kinetic energy does it have? Okay. So I'm just watching you guys to... Looks like you're good. So then, remember the equation for kinetic energy is 1/2 mv squared. So let's plug this stuff in. I have 1/2 times the mass times the velocity squared. Now this one I'm not as sure about doing in my head. 225. I think it's going to be 15,000? 150,000. Is that right?
135.
Oh, 135. Losing my touch. 135,000 joules. Okay, and then the second part asks, what if its speed were doubled? So instead of being 15, what if the velocity was 30? Now, if what I told you before is correct, for part 2, what that means is that kinetic energy would quadruple. If I double the speed, I quadruple the kinetic energy. So it should end up being 540,000 joules. And we could confirm that by taking 1/2 times the mass times 30 squared. So someone punch that in. I could already tell you it's going to be right.
Yeah, that's right.
Right. So this was our initial kinetic energy. Remember, if I double it, so this is for part 2. If I doubled it, then the kinetic energy quadruples. So you know where that comes up, you guys, on the exam. There's a good chance there might be a multiple choice question about that somehow, right? So don't mess that up. Okay. So I'm just waiting for everyone to look up. All right, looks good. So now let's get back to that definition of energy real quick. Right? We said that energy was the ability to do work. And actually, I'm impressed by you guys because usually when people give me definitions of energy, they try to use energy in the definition, right? Can't use something to define itself. Can't say like energy is energy. So anyway, we know that work and energy, they have to be related somehow, right? If energy is the ability to do work. So this is how they're related. It's something that's called the work-energy theorem. So the work-energy theorem, it's pretty simple. And what it says is that the work done on an object equals its change in energy. So the work done on an object equals its change in energy. So if we look, I just pulled out one of my utility bills, right? And like I said, this is one of the reasons why people know that there's a relationship somehow between energy and power, energy and work. But if you look at your electricity bill, you guys, how they bill you in kilowatt hours. Okay, kilo just means 1,000, right? So they're billing you. What are they billing you for? Well, um, watt is a unit of power, right? And isn't hours a unit of time? So they're billing you for power times time. Well, what? Wait, the equation for power was work divided by time, right? And if we solve for work, we would have to multiply both sides by t to get rid of it because it's being divided. Wouldn't work equal power times time? So what they're doing when they bill you in kilowatt hours, they are actually measuring the amount of work that was done by the energy on the appliances and all the other stuff in your house. Okay? So this energy was converted to work. You can convert between work and energy. Now, so when we say that the work is equal to the change in energy, like I could do work on an object and make it gain potential energy, right? These are examples of that. So let's say I have a roller coaster, and I'm making the motor on the roller coaster, I'm making it lift all of these people from the bottom here all the way up to the top. And so they're gaining potential energy. They're gaining potential energy. I could take their mass and I would times it by gravity, and then the change in height, that would be the change in potential energy, right? So the change in potential energy would be the mass times gravity times the change in height. Now, that is going to be equal to the force required to lift them up times the distance that they're lifted. Well, you guys, what force do I have to apply to lift something? You did it yesterday in your lab. The force would be equal to the... Yeah, I saw someone mouth it. Weight. It would be equal to the weight of the object, right? So if I'm lifting something, the weight of the object is the force. And then the distance here, isn't that just the same as height, right? Do you guys not remember, well, I know you do, that the weight of an object is mass times gravity, right? So this force would be mass times gravity. The distance would be height. Aren't those equations basically the same, right? They're like almost literally the same. So if I lift something up above the ground, I have to do work on it. That work is equal to the force times the distance. And whatever force I apply and whatever distance I raise it, that'll be equal to the change in potential, which is mass times gravity times change in height. Now this second one, this is actually pretty cool. Do you see all these windmills in the background here? So this is a wind farm in California. And I don't know if you guys have thought about it. I'm sure you have. Wind is not a steady state source of electricity, right? Sometimes the wind blows harder, sometimes it doesn't. And so there are times on these wind farms when they're not generating electricity, but people still might want to use it, right? So, and there are times on these wind farms when they're generating more electricity than people could use. So what they've decided to do out in California, and this is coming to other places, is they have these huge trains, right? And they funnel the extra electricity from the wind farm into the train, and they apply a force to it. They raise it to a certain height, and they increase the potential energy. And we'll get back to this when we talk about conservation of energy. But then they convert that back into electrical energy when they need it. So instead of having to use a battery to store the energy, they basically are using potential energy instead. We'll talk more about that, but it's actually pretty cool. Okay, now here's an example of a gain in kinetic energy by doing work. So in order to move a car, I have to apply a force, right? So I could measure the force between the tire and the road. Now, if I know the distance that the car moved, right, that force times the distance will equal 1/2 times the mass times the change in velocity squared for that car. So I'll show you, if we have time today, I'll show it to you, but I'm thinking I'll probably show it to you at the beginning of class on Monday. We have a video that shows that conversion and how we can calculate horsepower using change in energy. But that car, once again, that car can't move unless there's a force applied, and it's moved over a distance, and that force times the distance equals 1/2 mass times the change in velocity squared. Now let me ask you guys this: when you're cruising down the highway and you put the cruise control on, right? So you're going at the exact same speed. So let's say you're going down to check out U of I or Illinois State or, Eastern Illinois. Any of those places are all out in the middle of nowhere, right? And so you're going to be driving on this highway for a long time. So you just put the cruise on and, you're just steering the car, right? What's the net force? What's the net force that's applied to the car when you turn the cruise control on? So if you have the cruise control on, are you changing your velocity? Are you changing your kinetic energy? You're not, right? So the change in energy would be 0. So how much work is being done on the car? I'll give you a hint. It starts with a Z, right? Yeah, 0. There's no work. So the net force is 0. Now, why is that? Well, because the force that's pushing the car forward, that the engine's applying to push it forward, that's being counteracted by friction between the tires and the road and by air resistance, right? If there was no air resistance and there was no friction, then you would just keep getting faster and faster and faster, which is what happens with spaceships in outer space, right? Okay, so let's look at 2 problems. So here's problem number 1. I have a hockey player. His name might be Patrick Kane. He is applying a force of 250 newtons. And he's applying that force to a hockey puck. And the mass of the hockey puck is 0.12 kilograms. Okay? Now, if I measured how long he's applying that force, actually pushing on the puck, the distance is 0.8 meters. What I want to know, how fast is that puck going to be going when it leaves his stick? Well, you guys, what kind of energy am I giving this puck? It was stationary, and now it will be moving. So I'm giving it kinetic. Thank you. And so I know that the work done, which is force times distance on the puck, is going to equal the change in kinetic energy, which is 1/2 m delta v squared. Okay? Now, Patrick Kane, he can really get this puck moving. And I'll show you one of the reasons why. You see the bend in his stick? See how crazy that bend is? What that means is that he can keep his stick on the puck for a longer time. This kind of relates back to, remember first quarter when we talked about follow through? And I told you the longer you apply the force to the object, the faster it'll be going when it leaves, right? This relates back to that. So here we have a force of 250. We have a distance of 0.8. Then we have 1/2. Then the mass of the puck is 0.12 kilograms times change in v squared. And I could just put velocity squared because the starting speed is 0, right? So 250 times 0.8, that should be 200, unless I did something wrong. 1/2 times 0.12, that should be 0.06. Tell me if my mental math is wrong. You guys can always correct me. Then I'm right? Okay. So then we want to get rid of that 0.06, so we have to divide both sides by 0.06. That'll go away. Change in velocity squared. Now that one I can't do in my head. It's going to be 330. Wait.
I don't know if it was right, but I got 3333.3.
Yeah, that's what I was going to say. 3,333.3 repeating. And then take the square root of that, because I got to get rid of that squared. So then the change in velocity is going to be
57.73.
57.73 meters per second. All right. Now, I actually use very realistic numbers with this, you guys. The distance can vary a little bit. So what I did is I took the distance off one of his fastest slap shots. But if we look, it's 57.73 meters per second to miles per hour. That would be 130 miles per hour. So a typical slap shot that an NHL player can produce, it's like 100 miles an hour. It's kind of crazy to think about that projectile hitting you, which is why goaltenders wear like full masks, right? In the old days, goaltenders were missing a lot of teeth. But now they wear a mask. Hopefully they keep their teeth. Cool? Does that make sense? All right. Let's look at one more problem, and then I'll cut you guys loose. So I have a baseball, and it leaves a pitcher's hand at 95 miles per hour. That pitcher might be Lucas Giolito. Maybe. So the velocity of the ball, the change in velocity actually, because it's going from 0 to 95, the change in velocity will be 42.5 meters per second. So I just did the conversion for you. Once again, that's the speed of his average fastball. Okay. Now he applies a force to the ball for 50 inches. So that's the entire distance of his throw from back here to his release point. That's 1.27 meters. And the baseball has a mass of 0.145 kilograms. All right. What I want to know is how much force was applied to that ball. So if I want to solve that, I'm going to take force times displacement. That's going to equal 1/2 the mass times the change in velocity squared. Because here the work is going to equal change in kinetic energy. Okay, a bunch of people are looking up, but it looks like there's still a bunch of people writing. I don't want to go too fast. People yell at me already for going too fast when we're in person and I can see everyone. So I'm sure it was bad when I couldn't actually see your faces. Okay. So there's still a few people, but so then the force is what we're looking for. The displacement 1.27 meters. Okay, that's going to equal 1/2 times the mass, which is 0.145. Uh-oh. I have to move that. Times the change in velocity squared, which is 42.5 meters per second squared. All right. So I got to punch all of this in my calculator. 42.5 squared times 0.145 times 1/2.
130.95.
130.95. Nice. And then to get force by itself, I would divide both sides by 1.27. And the force will be... Wait, I'm sorry, what was that?
103.1.
103.1 newtons. There we go. So, if we converted that, you guys, into pounds, there are people writing, so I don't want to cover it up yet. Okay, so if I converted that, 100 and... Wait, what did we say it was? 103. 103.1 newtons to pounds. What? Why didn't it just give me the conversion? That would be 23 pounds of force. So you could see he's not actually applying a ginormous force to that baseball, right? And if you guys watch baseball or you play it, these pitchers pitch around 100 pitches per game. So it's not, the wear and tear isn't necessarily from the muscles, but this is a really violent motion, and he's throwing that ball at 95 miles per hour. So these pro pitchers, their arms, because their arm is moving basically that fast, it kind of pulls their arms slightly out of their shoulder, and it starts tearing at the tissue that's surrounding their shoulder. That's why they have to stop, right? And in high school, does anybody know what the high school limit is? I can't remember. Is it 60 pitches? Nobody plays baseball in this class? I'll have to ask Mr. Hammond. Mr. Hammond knows. So anyway, that is the work energy theorem. That's work, that's energy.